Do you have homework questions to go over? Yeah.
So for Jefferson, it's going to be like -7.
Oh, I already did that. Which one is it?
Jefferson and then the bottom one.
You wish to invest $5,000 for 4 years and you have 2 investment options. Bobby Kennedy Bank offers 3% compounded annually, while Jack Kennedy Bank offers 3% compounded daily. Clearly, it's all the way with JFK. Here we ask not what your bank can do for you. Instead, we ask you to analyze both options and determine how much more money you would have with Jack than with Bobby. Round the answer to the nearest cent. So the more frequently the compounding is happening, the more advantage it is to you earning the interest. What were there was daily, and what was the other one? Annually and daily. So we use 365. When we compound daily, we don't take into account what year. So for both of these, the principal is $5,000, and the rate is 3%, so 0.03. N is what is changing. So either one time per year. I think we're looking at over just 1 year, right? Oops. Oh, for 4 years. So if n is 1, then the arithmetic is pretty easy. Remember, we apply the exponent before we multiply times the 5,000. So 1.03 raised to the 4th power and then when you multiply times 5,000, and I'm not rounding off in my calculator like I did on the paper, so it's more digits in my calculator. So daily we have the same principal, but now n will be 365. You shouldn't round off in that decimal place at all when we're trying to compare. So I'm going to put 0.03 divided by 365. It's going to get a very tiny number. So there's an e -5. So 1, 2, 3, 4, 5. 5 decimal places we move our decimal. That means times 10 to the -5th power, and it moves your decimal 5 to the left. And then in the exponent, we have 4 times 365, 1460. So we add 1. And then we take that to the 1,460th power. So now I'll go ahead and multiply times 5,000. We have $5,637.46. So let's compare the two. So subtract the one from the other. So $9.92 difference in this case. So don't round off. Leave a lot of decimals there. You can see I left like a bunch of zeros and then 6 decimals after that. So you want to keep all those decimal places when you're working in just tiny little bits of numbers. If we had more time in the semester, we could look and see what a difference it makes if you round off than if you don't round off. It can be vastly different numbers. Anybody have any other questions? On your quiz, I know that you maybe round to different values, so I take that into account, and don't take off if you round differently than I did. Any other homework questions? Yes.
Mine's gave to infinity.
Okay. So suppose get that at the beginning of Party Animal Sam's student's college career, he deposits $200 into a savings account that earns 4% interest per year compounded annually. Exactly 10 years later, when Sam graduates, he closes the account. How much money in the bank does the bank give good old Sam? Round your answer to the nearest cent. $200, 4% compounded annually. 10 for 10 years. So we're going to find the final amount. $200 is the initial amount. The rate is 0.04. Compounding one time per year for 10 years, not 4 years. So we're just going to be adding 0.04 to the 1 and then raising that to the 10th power. So 1.04 raised to the 10th power is 1.48024. So the amount almost triples. Well, almost grows half again as much, I should say. Then you said number 3 also?
Mm-hmm.
Okay. Did you?
Because I was trying, like, I realized I meant to say section 3 and 6, because I've been trying to type things wrong. And
Okay.
I didn't understand, like, how to set it up.
Okay. I'm going to make these a little bigger so I can see them. So compounding grows from raising to powers. So 2 to the 3rd is 8, whereas 3 squared is 9. So in this case, 3 squared is bigger. So the arrow points at the smaller value, so we're pointing at the 2 cubed. But usually the exponent will make it bigger. So 5 to the 6 is bigger than 6 to the 5th, because I'm just guessing that. Let me just double check, but it should get to a certain point where the exponent is what makes the difference. Yeah, so 5 to the 6 is bigger because that exponent's bigger. So usually, if the exponent's bigger, that's the bigger value. So which is bigger here? N is bigger than M. N is bigger than M. So the author just put that first case in there to show you, well, if the numbers are little, then it's not always true. But with bigger numbers, it's this case. So you'd rather have 2 to the 100th power than 100 squared. Well, shouldn't that drop down and let me pick that? Does yours work on there? Okay, there we go. Let's see what number 6 is like. You wish to invest $4,000 for a year, and you have 2 investment options. Happy Bank will pay you 2% compounded annually, while Glee Bank offers 1.1% compounded quarterly. To maximize your income, which bank will earn you your business and give you a real smile? So you really should analyze both of these. So you would go through and use the formula. Just pick maybe a nice number to work with, like $1,000, and see which one gives you more money. Okay.
Okay.
Any other questions? Then let's go ahead and talk about your quiz. So your quiz is on Wednesday. We don't have class on Monday. You probably have other final exams during that period. Our quiz is like any of the other quizzes, is not cumulative. It's on the section since our last quiz. You can bring a 3x5 card. The time is a little bit different because the registrar sets those times. So we're meeting here at 10:30 to 12:30. If that doesn't work for you, you can meet with one of my other classes. I think it's ES 320. You can email me to check, or you can walk around. It's on the 3rd floor. You can walk around looking for me, whichever you prefer. Hopefully you had a chance to print out the review. So I'll ask you to split up into groups and work on this then in your groups. Does anybody have any questions before you work on your section that I assign you? Okay. So I'm going to have you work in groups of 2, possibly 3. So can you 2 please do 4.7? Mm-hmm. And can you 2 do 7.1, please? And then can you slide down and work over here? And can you two work on 7.3, please? And you 2 at 7.4. Instead of holding them, if you don't want to sleep, or you. Okay. What I do is 7.4. What's it for you? And you have 8.2. And then I'm going to ask you to work on 7.4. Someone's going to front one to
was just in one, so it's really nice. There was a one
So work in your groups for about 5 minutes, and then we'll work together for the rest of class. The Mindscapes, you should look in your book to see what they're on, because it's not always a Mindscape that I picked for your homework. No, that's
I'm just trying to
Oh, yeah. It's not bad.
I think it's a yeah. Which they're really similar to I just changed some.
Oh, it's $600.
Oh, I put it 200.
Yep, but that's exactly the right formula. Just figure it out.
Why did I put it 200?
Yeah, it's probably like 200.
If you get stuck, raise your hand and I'll come around and give you a hand, okay?
Okay, 618.
What's for the reading? Alright, then you can chapter. And then you just click chapter 11. And then scroll right down to find the Yep. This is the It is a fun. It's a tree. It's a tree branch or ferny leaf.
I have no idea.
Landscape 3 is two types of outlining scenarios.
Yeah, I think
There's a fraction.
you're not equal to it, are you? We are. Oh, no, they're equal to. No, you're not equal to, but you're equal. Okay, I'll come and try you. So, that's because I asked students to read that.
Well, 30 is asking us,
And then they
like,
were
as if there's a
gonna
picture there.
email me
Each
an
there is
example.
I'm confused when
We can
it's like how many.
Specific example.
How many edges does the
3 is by the time.
Yeah, you can do that in all three words.
there was an equation.
So you have to find
Sorry, it's been a hot minute to get it in.
So it's like, to make sure you know how to do this.
Yeah, this one is so those are
How you can make a bigger
Are you saying it's making this small?
I didn't give 9.1 to anybody, did I?
It's shrinking the bigger copy into little snippets. Okay.
4, 7.
Will you count the edges and the cubes?
There are. Yeah, I suppose. I don't know. There are 8 edges connecting.
Who had
So
7.4?
then when
Zach, you had 7.4?
Yeah.
Okay. You can just work on something.
Does anybody have 9.1?
9.1 was supposed to be done on your own, so I wasn't going to do that one in class.
Yeah.
Okay, so you have 4.7 cubes drawn?
yeah.
Almost don't want to.
Just confused how to figure out the edges.
Yes, I have a question.
So for the 3 iterations of the
Yes.
16.
So it's not the one on top.
How many edges are in cube? Multiply that by 2 and then every.
Yeah.
Because you have 1, 2, 3, 8 edges. 1, 2, 8. Plus the 8 here. 32.
Okay, so I will put your drawings up there for 4.7 if you have that.
Whoever looks better. Yeah. Because that one's a lot easier than that one to look at.
Yeah.
Okay.
There's like a lot going on here.
I think like the lines that connect.
So we'll go ahead and work together.
If
If you're not quite done, we'll finish it up together then. So the cube in 0 dimensions degenerated to a point. In 1 dimension, it became a line. In 2 dimensions, it's a square. And in 3 dimensions, it's the cube that you're used to thinking of. In 4 dimensions, we drag that 3-dimensional cube in a perpendicular direction somehow. Of course, we are trying to show that, and so we just show the cube, the 3-dimensional cube dragged to another position, and show it connected corresponding vertices. So back, right, top to back, right, top, front, right, top to front, right, top, and so on. So I will be checking to see that you connect corresponding corners, corresponding vertices, and I'll also be checking that there's 8 connecting lines that they connect to one another. Now if your lines happen to all fall on top of each other like this, then right off to the side there's 8 connecting edges, so that I know you know there's 8 connecting edges there. So how many edges did the 4th dimensional cube have?
I have 32.
Yep, 32. 12 on each of those cubes, and then 8 connecting edges. So that adds up 12 plus 12 plus 8, 32. How many vertices did it have?
A lot.
So those are the corners.
Yeah, we didn't get to that part
We
yet.
get to that part. There's actually 16, because there's 8 on each cube, so 8 plus 8. And then when you connect those, you're not adding new vertices, you're just connecting. Mindscapes 11 and 12 were to separate either some loops or some knots using the 4th dimension. Did you get to that one?
Mm-hmm.
Here's an example right here. So there's this knot, and we can use the 4th dimension to unknot it, or if we had links, if we had loops linked together, we could unlink them by lifting a piece of the rope into the 4th dimension. So we temporarily lift this little piece into the 4th dimension, and it disappears from the 3rd dimension. That's the point of what the 4th dimension is like for us who are in 3 dimensions. So if you were able to pick up a little piece of it and put it in the 4th dimension, it disappears from the 3rd dimension temporarily, and you can lift this loop all over top now and unknot it. Then once you've unknotted, you can put that loop back into the 3rd dimension. So lifting a little piece into the 4th dimension, it, quote, disappears from the 3rd dimension. You can unknot the ropes and then put the piece back into the 3rd dimension that was in the 4th dimension. Well, that brings us to 7.1. Did you come up with some natural items that have this sense of self-similarity that a fractal does? What was one of them?
A tree branch or a fern leaf.
A fern or a branch? Or even the tree itself, because then the branch looks like the tree. Great. Good examples. Let's see, Mindscapes 2 and 3, did you have to circle parts that look self-similar?
I think Mindscape 3 was circling the parts that look similar to
Okay.
the whole,
Okay.
the reduced version of it.
Okay. So here's a Sierpinski triangle. What part would you take that looks like the whole part?
Probably like one of those. It's like the top triangle.
This part?
Yeah.
Yep. So you could pick that part. So there's actually quite a few parts you could pick, aren't there? Could you pick this part?
Yeah.
So you could pick a lot of different parts there that look like the whole part. See if there's a Koch curve we can do the same thing with. Where's the picture of the Koch curve? Oh, here we go. So here's a Koch curve. What part could you circle of the Koch curve that looks like the whole Koch curve? Do you want to tell this one?
The first part.
The first part? So from here? Yep. How about, so this looks like the whole Koch curve. Could I pick this part right here too?
So,
Yeah.
on the quiz, are we gonna have to sketch it, or are we gonna have to circle it?
Both. And two different problems. So one will be circling. What part is similar?
So like we'll have to sketch one of these and circle the other one? Or do both for both?
There'll be two separate problems.
Okay.
So on this Koch curve, sometimes people circle from here to here. Is that part similar to the whole part? No, it's not. It's missing the flat side parts, right? And you could pick from here to here, but you can't just pick the peak. So that brings us to 7.2, and that's what we were discussing, drawing iterations of those curves. Did you, oh yeah, you showed me yours. I'm going to show them in the book because I have it right here though, okay. So the Koch curve, I'll just ask one iteration because that's more complicated. Whereas the Sierpinski triangle, I'll ask for 3 iterations. Okay. So you should be able to draw these. Draw these separately. Draw this separately too. Don't just draw it on top of the one that's given. Any questions so far? Okay, so that brings us to section 7.3 where we're looking at the dimension of the Koch curve, the Sierpinski triangle, and the Sierpinski carpet. So we're using either this formula or this formula. You should be able to get this correct so that your answer is in 1/100th of the number that you need to make the equation true. So you'll need one of these formulas on your card, on your 3x5 card probably, unless you memorize it. Let's take a look at the Koch curve first of all. So looking at the Koch curve, you need to know, first of all, what part would you use that you're going to make copies of and paste together to make the whole Koch curve. So you're going to think of what part you would use. Use the biggest part you can. So use this part. This would be one part you could use. So how many copies of this part do you need to paste together to make this whole shape? In group 7.4 group? Or 7.3 group? Oh, who's the 7.3 group? That's the one I missed. Okay. Does anybody remember then? How many copies of this do you glue together to make this whole shape?
Maybe.
Yeah, good. 4. 1, 2, 3, 4. 4 copies. So the number of copies needed is 4. Then the scaling factor is how much bigger this whole length is compared to the length that we made copies of. So this piece that we're making copies of is 3 centimeters. The whole length is 9 centimeters. How much bigger then is the whole compared to that 3 centimeter part? How many times bigger? You want to tell? Did you write that down?
It'd just be 3 times bigger.
Yeah, 3 times bigger. Yeah.
So you just plug that into your capacity equation.
Exactly. So the scaling factor is 3 times as long. And the number of copies is 4. So you fill that into the equation. And solve for 4. Now you can use this equation if you have a scientific calculator, but not everyone does. And so for this equation, I'm going to show you how to use guess and check. If whichever formula you use, make sure you write down at least the first step. So I know you know what you're doing and that you're not just writing down the numbers from class, okay? So the guess and check, you take 3 raised to some power, and you know it's not going to be 1 because 3 to the 1 is 3. But it can't be 2 because 3 to the second is 4. And that was the point of this section, that fractals fall between the dimensions. They're not the whole integer dimensions. So we'll guess some number between 1 and 2. That's too big. 1.5 is too big. 1.2 is too small. So I need some number in between 1.2 and 1.3. I'm trying to get 4 from this. So now I'm going to use a hundredths place. I'll say 1.25. That's closer. Let's try 1.26. That's only 1/100th away. Okay, so the 3.99 is 1/100th away, so I'll use that the dimension is 1.26. So you should have to go out to 2 or 3 decimal places here so that you're 1/100th away. The Sierpinski triangle, you'd work out a similar process. Let's see if I can find a nice picture of that. So the Sierpinski triangle, we'd look and see how many copies we need and what is the scaling factor. So take the biggest subcopy that you can. So take this whole big piece right here. This is what I'm going to make photocopies of. And if I make photocopies of this, I need 3 altogether. 1, 2, 3. And put them together, and that will make the whole shape. So the number of copies is 3. 3 copies of this can be put together to make a big Sierpinski triangle. When I do that, the original was 6 centimeters long. The one that I'm making is 12 centimeters long, so that's twice as big. Okay, so the scaling factor is 2. 3 copies to make a Sierpinski triangle twice as big. So scaling factor 2, and you can go ahead and use guess and check or use that other formula to find what B is then. Well, I'll get a picture of the Sierpinski carpet here, and you all try this one at your desk, please. The Sierpinski carpet is online. It's also pictured in your textbook back in chapter 1. So the Sierpinski carpet takes the center of a square out. We were taking the center of a triangle out for Sierpinski triangle. Sierpinski carpet removes the center square, and then you repeat that process again. So you can work with whichever iteration seems clearest to you. So think about which part you would take to make copies of. To make what are you going to make copies of and then paste together to make the whole shape? And how many copies do you need? And then you need the scaling factor. So if I'm just looking at this shape, I would take this piece, okay? Bottom left corner here. How many copies of that would you need? Go ahead and write down if you haven't yet. How many copies of this do you need to make the whole shape? Anyone want to tell what they got?
The number of copies.
Good, 8 copies. 1, 2, 3, 4, 5, 6, 7, 8. Remember, the yellow part's empty. 8 copies, and what is the scaling factor to go from this little one to the whole thing? From here to here. So it's 3 times as big, because you had 3 little squares, and now you have 9 little squares. So you take this little piece, again and again, 3 times as big. So the scaling factor is 3, and the number of copies is 8. Scaling factor 3, number of copies 8, and you can work on that, or you can, we did this in video too, you can look it on the videos. In 7.4, we talked about the Julia set. We had a nice website for that, marksmath.org/ let me get the rest of it. marksmath.org/visualization/Julia sets. So this is the Mandelbrot set, and we saw if we picked a point in the Mandelbrot set and clicked on it, the associated Julia set would come up. So every single point on the left that you click will give you a set on the right. Now if you pick a point right inside the black areas of the Julia set, then you're going to get a connected, I said it wrong. If you pick a point inside the black areas of the Mandelbrot set, you're going to get a connected Julia set. It's easiest to see in here. See how that's all connected? But if you pick a point that's not in the Mandelbrot set, well then the Julia set that goes with it is not connected. You get a bunch of scattered snowflake-like shapes. So here's a point not in the Mandelbrot set, and I get a bunch of scattered shapes. So with that in mind, let's look at the questions on the review here. Who had 7.4? You did? Okay. So if you pick a point, A plus BI, that is inside the Mandelbrot set, and use that point to build the A plus BI Julia set, how many pieces will the Julia set have?
I said that you would have 1.
1. Yeah. That's what you said, right?
Yep.
Okay. If you use the point A plus BI to build the A plus BI Julia set, and the Julia set has more than 1 piece, does that point you use lie inside or outside the Mandelbrot set?
That would be outside.
Outside. Good job. And so if you have a picture of a Julia set, as you saw a few on the screen here just now, you should be able to tell if the associated point with that Julia set is in the Mandelbrot set or not, based on if it's a one connected shape or a bunch of scattered shapes. Anybody have any questions? So the Mandelbrot set is made from all the points that make connected Julia sets. Who had 8.2? You had 8.2? Okay. And what did you get for the formula here for the definition of probability?
N divided by T.
N divided by T it is, yep. Did you write down what the N and the T are?
Hold on.
That's what I'm doing too. I'm going to look it up. Well, I'll just look it up and put it here.
N is the number of different outcomes to E. And then T is the total number of equally likely outcomes.
Good. Yep. So there's your definition of probability. Then you had the law of large numbers. So who's are you getting to do everything? Did you?
Yeah.
Yeah.
I'm in the bathroom.
Oh, okay. It's, I think that's suspicious timing. Okay. All right. What's the law of large numbers?
If an experiment is repeated a large number of times, then the relative frequency of a particular outcome will tend to be close to the probability of that particular outcome.
That's right. So if you do experiment in class hundreds of times like we did, the outcome should come to be close to the actual probability we calculated. And if we did it thousands of times, then it'd be even closer to the probability that we calculated, if we calculate probability correctly. So you'll also need to be able to make this chart with the 2 dice. We did that in class. You don't need to draw the little dots. You can just put numbers instead of little points. And then you can use that chart to answer questions. For example, at your desk right now, use this chart that I have up and calculate the probability of taking a pair of dice and rolling a 9. So what would be the probability of rolling a 9 with 2 dice? Anybody want to tell? Good, 4 out of 36, because there's a 9, another 9, 9, and a 9. So 4 out of all 36, 4 out of 36. So you'd write 4/36. Like that. Or you could reduce it, or you could write a decimal. It should be an answer between 0 and 1. If you just write the number 4, you will not get points. So these Mindscapes are those types of problems, looking at either dice or jelly beans or coin tosses. Those are all good types of questions for on the quiz. 9.1 you were supposed to read on your own. And I had told you that anytime up till today, so if you send me your 9.1 answers today, I'll tell you by the end of the day Monday if you're right or not. They're supposed to be specific examples from 9.1. Make sure you tell how that example distorts as it's presented, or tell how that specific example has been poorly collected. Okay, what makes it poorly collected? I think the Mindscapes in 9.1 give you some examples of that as well, I think. Who had 9.2? Okay, can you tell me the definition of what the mean is?
So you add up all the numbers and divide by how many there are.
Good. Add all the numbers and divide by how many there are. And how about the median? How would you calculate the median?
You would put all the numbers in numerical order and then it would be the middle number.
So put all the numbers in numerical order, and then the middle number is the median. We had a bunch of examples where there wasn't a middle number because we had even sets. What do you do in that case?
You would use the numbers, the 2 middle numbers, and you would add them up and then divide by 2.
Good. So if there's 2 middle numbers, add them up. And divide by 2. That's how you average the 2 middle numbers if there isn't just a single middle number. So we did lots of practice finding first quartile and third quartile. In fact, an easy example to find is right at the beginning of class on Wednesday, so you could use Wednesday's video if you want to practice finding those quartiles. So I need someone in your group's box and whisker graph and somebody's histogram. So somebody else, because you did all the answering. Who else has? You have a. Okay, that's it. Very nice. Okay. Good. So here's a nice little histogram. See how the scale is consistent? 0 to 50, 50 to 100, 100, 150, 150 to 200. So you need a consistent scale on both types of graphs. Then the left side would be frequency. And that's always labeled frequency. You see how there's a title on this axis too? Both your axes should have titles and a title for the graph itself. And then all the bars are put right next to each other. The reason there's no bars here is because there was no prices of houses sold in that price range. Excuse me. The box and whisker graph showed the 5-number summary. So you see another nice consistent scale, 0, 10, 20, 30, 40, 50. The median's drawn vertical, and the first quartile and third quartile are drawn vertical. Then you have the minimum and the maximum. You don't have to label min, max, and first quartile, third quartile, and median. That's unless if you do, I won't take off, but you don't have to. Then you have a title. There's no vertical axis at all on the box and whisker graph, but you do label the bottom axis. That brings us to chapter 10.3, and we actually will have this formula right on the quiz, but of course you'll need to know what all the letters stand for. We did do a couple of examples of that at the beginning of class. Would anybody like to do another example? Okay. Then we will call it a day. We got done a little bit early, so if you have questions and want to go over them after class, feel free to stay and we'll do that. Online students, feel free to email me. I'll see you on Wednesday.